Good morning, everyone. Today we will solve problems in chapter 14 about fluid dynamics. So let's start with problem 39. A large storage tank, open at the top and filled with water, develops a small hole inside at a point 16 meters below the water level. If the rate of flow from the leak is equal to 2.5 10 to the power minus 3 cubic meter per minute, determine the speed at which the water leaves the hole and the diameter of the hole. So let's start. We have here, I actually draw the hole, the tank as a rectangle, as you can see here, and this is the level of the water. So the given states that we have a hole which was developed on one side of this tank, which is over here, and this hole is 16 meters below the surface of the water. So here is the level of the water inside the tank, and this hole is below by h, where h is equal to 16 meters. Now, if the rate of flow from the leak is equal to 2.5 10 to the power minus 3 cubic meter per minute, determine the speed at which the water leaves the hole and the diameter of the hole. So let's start first by just commenting. When they say that the large tank is open at the top, that means that this surface is open to the atmosphere. So if you take any point on the surface, you measure the pressure. So the pressure measured at any point is nothing else than the atmospheric pressure, which is P naught. And then if the rate of flow from the leak is equal to this value, so the rate of flow, or in general also its flow rate, this is nothing else than the product between the cross-sectional area multiplied by the speed. So for example, if we, as we say here, the rate flow at the hole, so from the leak, which means that at this hole, the flow rate, it's nothing else than flow rate is equal to A2 multiplied by V2. So if you know the flow rate and you know one of these parameters, you can determine the other. So the first question, how much is the speed at which the water leaves the hole? So the speed of this point here when the water is leaving, how much is it? And you have to determine as well the diameter of the hole. طيب بأول سؤال we cannot use this equation that is the flow rate equals to A2 multiplied by V2. We know what it is the flow rate, or V2 is our unknown, but the problem is that A2 we don't know what it is, and it's also an unknown. فبالتالي بأول سؤال ما بنقدر نستعمل هالمعلومة اللي هي بالgiven which is that the flow rate is 2.5 10 to the power minus 3 cubic meter per minute. We have to find an alternative way to determine the speed. So one of the way is to use either the continuity equation or to use the Bernoulli's equation. But given what we have here from the given, actually all what we know is that we have this surface which is above the hole by h. We know that the pressure at the top is nothing else than the atmospheric pressure. So it's wise to take Bernoulli's equation and to apply Bernoulli's equation between 2 points. So one of the points should be at the hole, لأنه إحنا بالنهاية بدنا نجيب the speed of the water which is leaving the hole. فمن المنطق إنه ناخد إحدى البوينتس تكون على الهول بشكل إنه نقدر نستحصل على السبيد. البوينت الثاني لازم ننقيها بشكل منطقي، ولازم ننقي بوينت تكون بنعرف عنها اكبر قدر من المعلومات. فاذا ناخذ بوينت على السيرفيس of this of the fluid in this tank, we know the pressure, we know the height, so we know the elevation basically, يعني y, and okay, we still have the velocity. So let's take the point number 1 to be the point at the surface, and point number 2 to be the point at the hole. And if we apply Bernoulli's equation at points 1 and 2, we'll end up with P1 plus half rho V1 squared plus rho Gy1 equals P2 plus half rho V2 squared plus rho Gy2. So P1 is equal to P naught, so it's the atmospheric pressure, because as you know, the tank is open to the atmospheric air. So this is already known. P2 is also equal to the atmospheric pressure, because don't forget the hole here is open to the atmospheric air on the right. So this point is at the is in contact with the air, and so it is under the pressure of the air. So P2 is as well equal to the atmospheric air because the hole is up into the atmosphere. Now let's discuss Y position. So the Y, the elevation of these points should be evaluated with respect to a zero reference level. يعني أول شيء لازم ننقي شو هي level لما نحط عليها y equal 0 بعدين بنقيس على أساسها ال y1 and y2. من أفضل الطرق إنه to choose this y equals 0 level at one of the points. فبهالتالي نختصر بالايكويشن إحدى التيرمز وبيبقى عندنا التيرم الثاني. So if we take the level at the point 2 to be equal to 0 for the y coordinate, then y2 becomes 0 and y1 becomes h. So if we replace the pressure and the elevation by their values, we end up with P node plus half rho V1 squared plus rho Gy equals P node plus half rho V2 squared plus 0, because we have taken y at point 2 to be equal to 0, and therefore y1 is nothing else than h. So in this equation at the end, we can reduce P node from both sides. Rho Gh is known. V2 is the unknown we are looking for, but still we have a problem because V1 is also unknown. So at this point, it's quite useful to use the continuity equation, because the continuity equation, if we apply it between point 1 and point 2, it will give us A1 V1 equals to A2 V2. So we can deduce V1 as a function of V2. We replace it by its value in this expression, and then we get the unknown V2. So let's do it. So A1 V1 is equal to A2 times V2. Therefore, V1 over V2 equals A2 over A1. But the problem is that A2, it's quite small with respect to 1. In other words, ال A2 كتير صغيرة مقارنة بال A1. انتوا عم تحكوا عن خزان كبير وفي على جنبه فخذ كتير صغير. And this is clear in the given because they say a large storage tank develops a small hole. So just by saying these two words, it's enough to tell us that you can consider A2 very small compared to A1. And if it is the case, then V1 is very small compared to V2, which means that we can neglect V1. And if we neglect V1, we will end up with this equation. We end up with rho GH equals half rho V2 squared, as we have in here. We can reduce both rho on both sides, the density, and we end up with V2 equals 2GH with a square root. So if you make the numerical application, you will have V2 equals 17.7 meters per second. Now this is it. We could determine the speed at the hole, the speed of the water when leaking out from the hole. Now the second question was, we have to determine the diameter of the hole. So I remember the first discussion that we made when we were defining the flow rate. قلنا أن الفلو rate هو A times V. إذا بنعرف قيمة الفلو rate وبنعرف وحدة من هول الفاريبلز بنقدر نحدد الثاني. And actually in this case, so we know what is the rate of flow at the hole. So we know what is this value A2 times V2. We know what is V2, so we can determine A2. So let's write it down. The flow rate at the hole is given by A2 times V2. So we are talking about a hole. So this hole, it has a cross-sectional area. This is a circle, basically, we assume it. So it's equal to pi r squared. It's a cross-sectional area. And we are not requested to determine the radius, but we are requested to determine the diameter. So the radius is the diameter divided by 2. And so we end up with the flow rate equals to pi d squared over 4 multiplied by V2. On the other side, we are given the value of the flow rate. It's equal to 2.5 10 to the power minus 3 cubic meter per minute. So this is per minute, and we cannot use it. We have to convert it to cubic meter per second because we need to be consistent in our calculation. So that's why we have to divide by 60 seconds, and we end up with this value. Finally, from this equation, you can write down d squared equals 4 multiplied by the value of the flow rate divided by pi multiplied by V2. And whenever you want to get rid of this the squared, you have to make a square root here. So we end up with the value 1.73 10 to the power 3 meters, which is equivalent to 1.73 millimeters. And so as you can see here, this value is quite small with respect to the value of the cross-sectional area at the surface. يعني عمليا هذا القيمة كتير صغيرة مقارنة بمساحة الخزان كسيرفس من فوق. فهذا الشيء بأكد لنا انه الاسامبشن او الابروكسيميشن اللي عملناها لما اشتغلنا بالcontinuity equation is true and it's valid as well. So this is it for this problem. Let's move on with next problem. A legendary Dutch boy saved Holland by plugging a hole in a dike with his finger, which is 1.2 centimeter in diameter. If the hole was 2 meters below the surface of the North Sea with a density 1030 kilogram per cubic meter. A, what was the force on his finger? And part B, if he pulled his finger out of the hole, how long would it take the released water? So if you have, this is the released water comes out from here. How much would it take this released water to fill in 1 acre of land to a depth of 1 foot? So basically قد ايه بدكم وقت لحتى تعبوا عمليا كميه equivalent ل 1234 cubic meter in 1 year. So this is it. Let's start. هون شو عم يصير عنا عمليا؟ في عنا سد. So هالسد في عنا من هون water أو yeah we have a North Sea, so we have sea water, and you have a boy who puts his finger inside, or he tries to dig into the wall of the dike بهالشكل. So حفر وبالتالي هدي إصبعه جوا. The first question هي what was the force on his finger? So قد ايه هي الفورس يلي على إصبعه عم بتكون كبيرة. So let's see first what is the force exerted on his finger because of the water. Because you know his finger stands at this point, and so you have pressure from the water on one side and you have the pressure from the atmospheric air on the other side. So let's see what is this force F just due to the water inside this container أو بقلب هيدا السد، وبعدين حنشوف حسب قيمتها وبعدين نرجع بنشوف من تاني جهة شو عم بيصير. Okay, so we know that the force is equal to the pressure multiplied by the cross-sectional area. This is simply reduced from the definition of the pressure, which is given by the pressure is equal to the force divided by the cross-sectional area. That's number one. And we know that the cross-sectional area for a given hole, so a hole is assumed to be circular or just modeled as a circle. And so it's equal to pi multiplied by r squared. But since here we don't have the information about the radius, but we know the information about the diameter, so we are going to stick to the diameter, and so we are going to write this is pi multiplied by the diameter divided by 2 squared. So we know what is the expression of F, we know the expression of A, so therefore we can now make it. What do we need still? We need the pressure. So in order to determine how much is the force, we have to determine what is the pressure at point 2. So in order to do so, we have to use the Bernoulli's equation between the 2 points. Point 1 on the surface of the water on one side, and the point 2, which is the point at the finger of the boy. So at the point where the boy has done a hole. بس انتبهوا بهالسكشن الصبي فقط السد ولكن بعده اصبعه جوا، يعني عمليا هون بعده ما عم يتحرك المي ولا من فوق ولا من تحت. So let's take this points 1 and 2 and let's apply Bernoulli's equation on these points. So we end up with P1 plus half rho V1 squared plus rho GY1 equals to P2 plus half rho V2 squared plus rho G times G times Y2. Now, the pressure at the surface at point 1 is nothing else than the atmospheric pressure. So this is it. This is atmospheric pressure. Then we have half rho V1 squared. This is equal to 0. for the simple reason that yet there is no motion for the fluid, in the sense that the hole is still plugged. Plus rho times g times y1. So we need to specify a 0 reference level. So if we take the reference at point 2 to be our reference for the elevation, then we end up with y2 equals 0 and y1 equals to h, where h is equal to 2 meters. So we know everything about it. So plus rho gh is equal to the pressure at the point 2, we don't know what it is, we are looking for, plus half rho v2 squared, also this is 0, because the fluid at this stage of the question, it's still not leaking out, plus the 0 for y2, because we have taken y2 to be our reference level. So we end up at the end with P2 equals P node plus rho times G times H. But okay, so this is the pressure at this point 2, and therefore this is the force. Now the point is that هالنقطة هذه اللي هي على ال2 واصبعه للصبي عم يتعرض لضغط المي من أول جهة اللي هي جبناها هي عمليا P2، بس كمان عم يتعرض لضغط الهواء من ثاني جهة. So basically عم يتعرض من هاي الجهة لضغط المي وعم يتعرض من الجهة المقابلة لضغط الاير. So on one side you have P2 and on the other side you have the atmospheric air. So in order to determine correctly the force, you have to take into account that the buoy is experiencing the atmospheric air on the pressure on the other side, and in opposite direction with respect to the pressure of the water. يعني ال pressure of the water جاية من الجهة الشمال باتجاه اليمين، بينما الاتموسفيريك air عم تعمل ضغط باتجاه الشمال من اليمين. So that's why we have to put a minus sign here between P2 and P0 and or P node. And so the force, the final force, is equal to P2 minus P node multiplied by A. But this equation already gives the value of P2 minus P node. So P2 minus P node, according to the Bernoulli's equation between points 1 and 2, it's given by rho times G times H. So we replace this P2 minus P node by rho GH in this equation where we are evaluating the force. And A, we already have written it. It's pi d squared divided by 4, where d is the diameter of the hole. We replace each term by its value, so we end up with this value of the force. So the finger of the buoy is experiencing this net force with the value 2.28 Newton. So this is it for the first question. Now I would just want to highlight one thing. So we can also solve this problem in a little bit different way, in the sense that we can say that, so here is the dike, and this is the here is the finger of the buoy. So the finger of the buoy is experiencing basically two forces. The force from one side was the force exerted by the water on the left on the finger of the buoy, and we have on the other side the force exerted by the atmospheric air, which is on this side. لأنه مثل ما بتعرفوا على طول الفلويد it exerts a normal force on the surface of contact ما بينه وما بين الأوبجكت وبتكون باتجاه الأوبجكت نفسه. So according to Newton's law, we can write down that the sum of external forces is equal to m times a. And of course, here we can take only the x direction, because both forces are horizontal. So we can write down sum of x equal to m times ax. Okay, but the finger of the buoy is not moving, so this is equal to 0. I mean, yet the buoy has put his finger in the hole وبعده الفينجر جوات الهول، بتاني بارت بيشيله. That's why هون بنحط ال ax equal to 0. So what about the summation of fx? If you just project this fw and f air, so we end up with f water minus f air is the total force exerted on the buoy. Okay, no, so sorry. Here I just discussed this. No, we don't know actually what it is, the acceleration. I'm sorry, I just forget about this detail. we are looking for this resultant force along the x-axis. So F water is nothing else than the P applied by the water, okay, I will call it like this, multiplied by the cross-sectional area of the hole, minus the force exerted by the air as well is nothing else than the pressure, which is the pressure of the atmospheric air multiplied by the cross-sectional area A. So the pressure exerted by the water on this point, we call this point 2. So this is nothing else than the pressure P2. So we end up with P2 minus P node multiplied by A. And so we can deduce that the force exerted on the boy's finger is given by F equals to P2 minus P node multiplied by A, where P2 is the pressure of the water at the point 2. So فينا نحكي بهالشكل، بنرجع بنقول we will determine what is P2. بنجيب من هون ال P2 بتطلع معنا P node plus rho GH، نطبق يعني مثل ما طبقنا النيوتن، مثل ما طبقنا عفوا Bernoulli's equation، وبتطلع معنا بالاخير هيدي الفاليو. Okay. So we continue with the second question. The second question is, if the boy pulled his finger out of the hole، يعني عمليا هلا سحب اصبعه من الهول، قد ايه بده وقت المي اللي طالعه من الهول اللي عم تتدفق من هالنقطه هيدي، قد ايه بدها وقت لحتى تعبي مساحه عباره عن 1234 متر مكعب. So 1234 cubic meter. This is the question. Okay. So let's start. The amount of time needed. نحن شو بدنا نجيب؟ بدنا نجيب قد ايه بدها وقت لحتى يعبي هالمساحة اللي هي 1234. So 1234 cubic meter. Okay. So if we want to know how long does it take لحتى المي اللي طالعة من هالهول إنها تعبي هيدي المساحة كاملة. So in order to determine this, okay, we need to determine what is the flow rate at this hole. يعني قد ايه معدل تدفق المياه على هالهول، وبعدين بنقدر نحسب قد ايه بده وقت من خلال انه بنقسم المساحة الكاملة divided by the rate of flow. Okay. So that's why we will need actually to determine the rate of flow. So to determine the rate of flow, we need to determine A2 times V2. So A2 is in principle known because we know what is the value of the diameter of this hole, but we don't know what is the value of the velocity at the hole. So هون المي عم تتدفق ب given value V2, and we don't know what is V2 or how much is V2. That's why we need to apply Bernoulli's equation between this point 2 in principle and another point, which let's take it to be at the surface again, because at the surface we know, I mean, if you take the point at the surface, we know a lot of information. First of all, we know that the atmospheric pressure is the pressure at point 1. We know that the point 1 is at a given height h with respect to the point 2. So there are a lot of information that we can get out. So let's apply Bernoulli's equation between or to points 1 and 2. We end up with P1 plus half rho V1 squared plus rho GY1 equals to P2 plus half rho V2 squared plus rho GY2. So let's now make some analysis. So first of all, now the finger is out، يعني ما بقى هون في إصبعه للصبي صار برا، وصارت المية عم تتدفق بهالاتجاه. So first of all, the pressure at point 1, it is nothing else than the atmospheric pressure, because of course this is even not a tank، هيدا سد مفتوح على الاتمospheric air. So P1 is equal to P atmospheric P node. كمان هلا صرنا على نقطة 2، كمان النقطة 2 صارت مفتوحة للاتموسفيريك air من جهة اليمين. So also P2 is equal to the atmospheric air P node. So that's why we can reduce P1 and P2 on both sides. Then if we take the level at point 2 to be the y equals 0 level, then we can say that y2 is equal to 0 and y1 is nothing else than h, just like before. So we end up with y1 equals to h and y2 is equal to 0. So we end up with the following equation: half rho v1 squared plus rho gh equal to half rho v2 squared. Now, we don't know what is v1 actually in this case. We know that v1 is pointing downward and it has some value. So this is V1, and we know that the water is leaking out at the hole with a speed V2. But given that actually between point 1 and point 2 we have a very big difference between the cross-sectional areas, yani A1 is quite big and quite large compared to A2. Therefore, we can deduce from the continuity equation that V1 is quite small and very much small compared to V2. And therefore, we can neglect V1. So this could be neglected relative to V2 أو بالنسبة ل V2. And so we end up with rho GH equals half rho V2 squared. So V2 is equal to square root of 2 times G times H. And we end up with a value 6.26 meters per second. So if you know what is the value of V2, now we can determine the flow rate. The flow rate is equal to A2 times V2. We replace all the parameters with their corresponding values, 1.2 centimeter for the diameter. So don't forget to convert from centimeter to meter. Multiplied by the velocity magnitudes or speed, 6.26, we end up with this value for the flow rate. Now, the time needed to fill this 1,234 cubic meter, it's given by this whole volume divided by the flow rate, which is expressed in cubic meter per second. So we end up with the value 1.74 10 to the power 6 seconds, which is equivalent to 20.2 days. So if the water is flowing out of this hole with the value 6.26 meters per second, then we will be able to fill this 1,234 cubic meter in almost 20 days. So this is it for this problem again. The only thing that is new in this problem with respect to the previous one is that you had to deal with forces. And I mean, it's quite easy to deal with forces in this perspective. Just think about the fluid that is making a pressure on the object. And for each fluid, you will associate a pressure, and then you will associate a force. And of course, you know that the force is all the time perpendicular to the object, to the surface, or to the point where the object is in contact with the fluid. And in magnitude, it's equal to the pressure multiplied by the cross-sectional area. So let's move on with a new problem. We have here a pipetted tube. So a pipetted tube, it's kind of standard in the fluid dynamics. And so you need to know in general what we mean by a pipetted tube. So a pipetted tube can be used to determine the velocity of airflow by measuring the difference between the total pressure and the static pressure. So it's actually shown in this figure as it is in the book. However, I here just drawn another figure, which is quite easier to understand than the one in the book. So here what you have is a flow of air. So this air, of course, it's moving with a given speed. Now, you insert inside this flow a U-tube. And this U-tube, it includes the mercury inside of it with density 13,600 kilogram per cubic meter. What happens is that because of the pressure coming from the air, there will be some difference. The mercury will move, and then there will be a difference between the level of mercury on one and the other side of the U-tube. So the question is, if the fluid in the tube is mercury, with a density, as we said, 13.6 10 to the power 3 kilogram per cubic meter, and delta H, which is the difference in the level, in the mercury level between the right-hand arm and the left-hand arm of the U-tube, if delta H is equal to 5 centimeter, you have to find the speed of the airflow and assume that the air is stagnant at point A and take rho air to be equal to 1.25 kilogram per cubic meter. So first of all, we have to determine the speed of the airflow. So we have to determine V air. That's number one. And then number two, well, in terms of comments, بقولكم assume that the air is stagnant at point A. لما قولكم point A is, لما قولكم the fluid is stagnant at point A او ممكن يقول لكم انه A is a stagnation point. هذا الشيء بيعني انه the speed of the fluid at the point A where there is a stagnation is equal to zero. يعني عمليا هون at the point A الفلويد ما عم يحرك. اللي بيصير انه الفلويد بيجي من هون اللي هو بهالحاله الاير، فبفوت بقلب اليوتيوب and then بصير بشكل انه بس هون اليوتيوب بيتعبى with the fluid, with the corresponding fluid اللي هو air, and it does not move any longer. So at this point the speed becomes just equal to zero. So the question is, we have to define and we have to determine the speed of the airflow. So what is the air? Okay, so of course here the obviously, and the obvious thing is that we can determine the speed of the air because of the pressure which was measured in this YouTube. يعني عمليا اللي عم بيصير انه حسب سرعه الهواء هل ميركوري حيتحرك، وبالتالي هون احنا اللي بيصير بالاخير انه بنقيس الفرق البريشر ما بين البوينت A وما بين البوينت B، علما انه البوينت B عن البوينت A الفي السبيد عليها هو صفر. So first of all, point A is one of the points to be used because we know at least the speed at point A is equal to zero. Now let's choose another point of relevance and where we can apply also Bernoulli's equation. بالنهاية نحن هون بحاجة للسبيد، يعني بحاجة لإيكويشن فيها speed. So it could be the continuity, it could be Bernoulli. But in principle here we are measuring the speed based يعني على أساس الفرق بالميركوري column ما بين الكولوم يعني الليفت والرايت arms بقلب هذا اليوتيوب. يعني عمليا نحن نعرف some pressure difference delta P. فشو هي الايكويشن اللي بتجمع البريشر مع السبيد؟ هي البرنوليز ايكويشن. So بنطبق برنوليز ايكويشن at 2 points. The first one is the point A. هلا فينا نلاقي ثاني بوينت مثل ما بدنا، بس بحكم انه برنوليز ايكويشن just to remind you فيها the term pressure plus half rho v squared plus rho times g times y. فمن الحكمه انه ناخذ الثاني نقطه تكون موازيه لنقطه A، بمعنى انه يكونوا both at the same level، لانه اذا كانوا اثنيناتهم at the same level ساعتها بنقدر نتخلص من احد التيرمز بالبرنوليز equation. So that's why let's take point B to be at the same level as the point A, where point A is the stagnation point, and let's apply Bernoulli's equation at these points. So we end up with PA plus half rho VA squared plus rho GYA is equal to PB plus half rho VB squared plus rho times G times YB. So we have chosen A and B to be at the same level, so we can simplify or reduce the term rho gy on both sides of the equation. Rho gy بنتخلص منها بيبقى عندنا بس PA plus half rho VA squared equals PB plus half rho VB squared. بعدين ال A بما انها هي stagnation point ال V عليها هي صفر, so we end up with PA minus PB is equal to half rho V air squared. That sounds great. This is our unknown, and we still need to determine what is PA and PB. Type. In principle, the pressure difference between points A and B should be easy to determine. How? Because you all know how now to deal with a YouTube, you know. انا بدي اكسس على البوينت A والبوينت B، وبهذا اليوتيوب بعرف انه في عندنا ميركوري، وهالميركوري طلع بشكل انه قاس فرق الضغط ما بين اول كولوم والثاني. So if we take this point to be, let's call it point M, to be at the separation at the surface between the mercury and the air, and let's take another point which we are going to call, for example, point N, to be at the same level as point N, such that the pressure at both points M and N, they are equal, because those 2 points, they are 2 points in the mercury and they are at the same level. What about point M? How much is the pressure at point M? Okay, according to the relation of hydrostatic, the fundamental relation of hydrostatic, we know that the pressure at a given point, like in this case the point M, it's equal to the pressure at the top point where the pressure is known. فالنقطة الأقرب اللي بنعرف عليها شو هي البريشر هي البي اي، وإحنا أصلاً ما بنعرف البي اي، بس إحنا بحاجة إنه نعمل access على البي اي. So we are going to take the point A on top of the point M. So the pressure at point M هي PA plus the pressure exerted by this row of air, right? By this column of air, pardon. So we end up with rho air multiplied by G multiplied by, I will call it H air at the moment, or yeah, let's call it just H. So let's call this H. Okay, in the same way also, we can write down the pressure at the point N. It's given by, again, we go to the highest point where the pressure is known, which is point B. And we also need the point B. نحن بدنا نجيب PA minus PB. So أنا حكما بدي طلع ال PA وال PB بالاكسبريشنز تبع ال M وال N. يعني البريشر على ال M وعلى ال N. وبنفس الوقت بدي 2 points يكونوا بقدر اربطهم ببعضهم، لها سبب اخذتهم على نفس المستوى بقلب اليوتيوب. So PB plus. Now we have the let's say the pressure of the mercury exerted by this column of mercury. So we end up with rho mercury multiplied by G multiplied by delta H, right? Plus rho of the air, الفوقة في air, multiplied by G multiplied by. Now how much is column here? It's given the height of this column. It's H minus delta H. Let's call it H minus delta H مباشرة. So since PM is equal to Pn, so we can write down PA plus rho air times G times H is equal to Pn is given by Pb plus rho of the mercury times G times delta H plus rho of the air times G times H minus rho of the air times G times delta H. So as you can see in here, rho air times G times H, and here we have rho air times G times H. Those are, they can be reduced on both sides of the equation. And so we end up with PA minus PB. ناخد ال PB لتاني جهة. بصير في عنا PA minus PB equals to. Have a look here on the right hand side of the equation. We have delta H in the first term and delta H in the second term. So فينا نجمعهم سوا نحط in fact a common factor. And so we end up with rho mercury minus rho air multiplied by G multiplied by delta H. And so this is it. We determine the difference in the pressure between points A and B simply by using the information of the, well, which is given in the YouTube by this difference in the mercury level. طلعت معنا rho mercury minus rho air as a factor multiplied by G multiplied by delta H. إذا بتحطوها بقيمتها بهيدي الإيكويشن تقدروا تجيبوا مباشرة صرتوا ال V air. So this is what we are going to do. So here I've just written everything as it is. We end up with, so therefore, rho of the air is equal to, yeah, so it's equal to 2 times rho mercury minus rho air in principle times G times delta H. However, here I just made the simplification because the rho of the mercury, it's equal to 13.6 10 to the power 3 kilogram per cubic meter, and rho of the air is nothing else than 1.25. So there is a big difference between these two quantities, and so we can neglect rho air with respect to the density of the mercury. That's why the difference in the pressure, we just wrote it as equal to rho of the mercury times G times delta H. بنحطها بنرجع بقيمتها بالايكويشن البرنولي. And so we end up with V air equal to square root 2 rho the mercury times G times delta H divided by rho of the air. And so you end up with the value 103 meters per second. So this is it for the pipette tube. The pipette tube, you should know how it works. And it's quite easy. You always have a stagnation point in the pipette tube so that the fluid does not move any longer on this point. And because of that, you could measure the speed of the flow at another point. So this is it for the problem 49. Let's move on and continue with this problem. So problem 53, a hypodermic syringe contains a medicine with the density of water. So basically in this syringe you have medicine, but it has the same density of the water. So the barrel of the syringe has a cross-sectional area, capital A. So this the big cross-sectional area is given by 2.5 10 to the power minus 5 meters squared. And the needle has a cross-sectional area which is given by 1 times 10 to the power minus 8 meter squared. In the absence of a force on the plunger, the pressure is everywhere equal to 1 atmosphere. بدون ما يكون في ولا أي force F عملياً، البريشر بكل النقاط هي عملياً حتكون P atmosphere. Now, if you apply a force F of magnitude 2 Newton, when this force acts on the plunger, making medicine squirt horizontally from the needle. So if you apply a force F, which is 2 Newton, then the medicine will get out from the needle. The question is, determine the speed of the medicine as it leaves the needle tip. So لما تطلع من أعلى النيدل قد إيه حتكون ال V of this medicine. So again, here we are in the same situation where we need to determine the speed of the fluid, given that you have actually you have applied some force, some external force on the plunger. So let's take 2 points. Let's consider this picture in here. So we need to determine the speed at this point. So let's take this point to be the second point where we want to apply the Bernoulli's equation. The first point should be chosen in such a way that على point 1 لازم يكون في عندنا access على الفورس F، وكمان لازم تكون هيدا البوينت 1 at the same level as point 2 لحتى نختصر one term بالبرنولي's equation. And so that's what we do. Let's choose point 1 to be at the surface of the plunger from inside, and point 1 and point 2 to be at the needle. And we apply Bernoulli's equation between these 2 points. So we end up with P1 plus half rho V1 squared plus rho times G times Y1 equals to P2 plus half rho V2 squared plus rho times G times Y2. Now, how much is the pressure at the point 1? طيب نحن قلنا هو انه قبل ما نطبق اي force على البلانجر, in the absence of a force on the plunger, the pressure everywhere is 1 atmosphere. يعني إذا بيجي بتطلع على هالpoint 1, the pressure at the point 1, it's simply given by the P atmosphere, P node, زائد delta P, زائد قد ايه نضاف على هيدي البريشر بحكم انه كان في عندنا force. وهيدي الدلتا P قد ايه هي عمليا the force divided by the cross-sectional area, where delta P هي عمليا البريشر مثل ما بنعرف هي الفورس على الاريا. So this force is nothing else than the 2 Newton which was applied on the plunger. والA هي the cross-sectional area تبع البلانجر. So we end up with first P1 is equal to P node plus delta P, with delta P equals to, if you make the numerical application, you end up with 8 10 to the power 4 Pascal. Now the second question is, so we need to determine this V, right? But well, in the equation we also have V1, as you can see. So of course rho GY1 and rho GY2 we can get rid of them because both they are at the same level, both points. So what about V1? Again, we use the continuity equation between points 1 and 2. So we end up with A1 V1 equals to A2 V2. Therefore, V1 is equal to A2 over A1 multiplied by V2. So if you just make the numerical application, because here we have the numerical values of A2 and A1, so we can make the numerical application, you end up with V1 equals 4 10 to the power minus 4 V2. طيب already كتير صغيرة مقارنة بالV1 رقم 1. رقم 2 نحن بالايكويشن مش بس عندنا V1، نحن عندنا V1 squared. يعني إذا ال V1 كانت proportional at 10 to the power minus 4 V2, فال V1 squared is proportional to 10 to the power minus 8 V2 squared. So V1 squared is really very negligible compared to V2, and so we can neglect this term inside the equation. Now we still have, so we already get rid of this term. V1 squared, we said it's negligible. We determined the value of P1 وبقى عندنا غير ال P2. But actually this point 2 is open to the atmosphere. So the pressure at point 2 is nothing else than the atmospheric pressure. So if we substitute each term by its value, you end up with P node plus delta P plus 0 for the half rho V1 squared because it's negligible. It's equal to P node plus half rho times V squared, where V here is the speed of the fluid at the needle, which we have written it earlier to be V2 squared. So P node and P node on both sides, they cancel out. And so we end up with V equals square root of 2 multiplied by delta P divided by rho, which is given by 12.6 meters per second. So at the end, we deduce the value of the velocity when the fluid goes out at this point at the needle, and we found that the speed or the magnitude of this velocity is given by 12.6 meters per second. So this is it for this part of the for the first part of the problems about fluid dynamics. I will stop here, and then in the next video you will have the other list of problems, and we are going to solve them together.